There's two major types of log equations that you might see, and one type is where you have a log on one side and a number on the other side. Now to solve these, you really need a single log on both sides. So what I need to do is I need to figure out a way to write this difference of these two logs as a single log. And fortunately I have log properties that allow me to do this, because if you'll remember, we have the property that says if you have the log of m minus the log of n, then that's equal to the log of m over n. So I can write the left hand side as a single log of 2x over x minus 3, and then I just bring down the number on the right. Now I can convert this to exponential form, because remember, this is a common log, so it's understood to have a base 10. So now I can convert this to exponential form by just saying 10 to this power, 10 to the first, is equal to this argument, which is 2x over x minus 3. Okay, so there I have 10 equals 2x over x minus 3. So then all I have to do is multiply both sides by x minus 3 to get rid of the denominator. And if I multiply, if I do that, then on the left I'll have 10 times x minus 3, which I show right here, and then on the right the x minus 3's will simply cancel out here, and I'll just get 2x. Well, then I can solve this. This is just a linear equation, so distribute the 10 here and I get 10 times x is 10x, 10 times minus 3 is minus 30, and then bring down the 2x. So now all I have to do to finish this is just subtract 2x from both sides. So take 2x away here, and then of course take 2x away here, and 10x minus 2x is 8x, and then of course over here these cancel. And the other thing I can do is I can add 30 to both sides, so just add 30 here, or if you prefer, just move the 30 over and change the sign, but basically if you add 30 to both sides, you'll get 30 on the right hand side. So I get 8x equals 30, and then to solve for x, just divide by 8. And so when I divide this, I get 15/4 or 3.75 for the answer. And you need to check these when you're solving log equations, because what could happen is you could get a number that's not in the domain of these logs. So remember, for these logs, the 2x must be a positive number and x minus 3 must be a positive number. And so let's check and make sure both of these are positive. Well, if x is 3.75, 2 times 3.75 is a positive number, and 3.75 minus 3 is a positive number, so 3.75 is a valid answer. Okay, now the other type of log problem would be where you have a log equal to a log. Now again, on this side I don't have a log equal to a log. I've got a log equal to the sum of two logs. But you know that you can write the sum of two logs as a single log using your log properties. So we'll take this log and write it using the log property. Remember, if you have the log of m plus the log of n, you can write it as the log of m times n. So I'm going to write this log as the natural log of 2z plus 2 times z minus 2. And now, since I have a log on the left equal to a log on the right, remember we had a property that said if you have the log of m equals to the log of n, then m must equal n. So since these two logs are equal, their arguments must be equal. So 3z plus 8 must equal 2z plus 2 times z minus 2. And now I just solve this quadratic equation. So go ahead and FOIL these two together to get the product to be 2z squared minus 2z minus 4. And then just subtract 3z and 8 from both sides. So if you take 3z away over here, it's just going to cancel those two terms. And then if you take 3z away over here, you'll get minus 2z minus 3z, which is going to give you this minus 5z. And also we subtract 8 from both sides. So when I subtract 8, the 8's cancel, and then subtract 8 from this side, and minus 4 minus 8 gives me minus 12. So I end up with 0 on the left and 2z squared minus 5z minus 12 on the right. And now to solve this, I can either use the quadratic formula to solve it, or I can factor it if it'll factor. And it turns out that this does factor into 2z plus 3 and z minus 4. So if I set 2z plus 3 equal to 0 and solve that for z, I get z equals negative 3 halves. And if I set z minus 4 equal to 0 and solve for z, I get z equal 4. Now the problem though is z equal 4 works fine because 3 times 4 plus 8 is a positive number, 2 times 4 plus 2 is a positive number, and 4 minus 2 is a positive number. But negative 3 halves, that's negative 1 1/2, it'll probably work fine here, and it might work, let's see, it doesn't work here because if you plug negative 3 halves in here, you get negative 3 plus 2, so that would give you a negative argument. And also it wouldn't work there, but it doesn't matter. If it doesn't work in one of them, then it's not going to work. So z equal negative 3 halves would not be part of the solution because it's not in the domain. So therefore the only solution would be z equals 4. Okay? Now, let's take a look at a couple more. And these are what I call non-traditional log equations. But on this one, you have the log of x cubed. And this I can actually write as 3 times the log of x. But I can't do this one because this is different. This is the log of x quantity squared. So it's not the same as what I'm doing over here. Here I'm cubing the x, then taking the log. But here I'm taking the log first, then raising it to a power. So this side is just log of x quantity squared, and this is 3 log of x. But what I can do is I can take this term and move it to the other side, and it'll become minus that term. And then I have a common factor of log x. So you'll notice I have here, this is like log x times log x, right? And then this is log x times negative 3. So if I factor a log x out of both these terms, so there's the log x I'm going to factor out, that if I factor the log x out of this term, I'm going to be left with a log x. And if I factor a log x out of here, I'm going to be left with minus 3. So then I know that the only way this product can equal 0 is either the log x has to equal 0 or the log x minus 3 has to equal 0. So let's solve each of these equations independently. So on this one, remember the base of this log is 10. So on this one, we can write this as 10 to the 0 equals x, and 10 to the 0 is 1. So the solution for that one would be x equals 1. Now this other one, first thing I'm going to do is isolate the log term. So I'm going to get log x equals 3, and then I can solve that the same way I solved this. The base here is 10, so that would be 10 to the 3rd power equals x if I put it in exponential form. And so that would be 10 cubed equals x, so x would equal 1,000 because 10 cubed is 1,000. And so there's your solution for those two. And you can check them, but they do check. Now this is an interesting one here because here the unknown is the base. But what we can do here is, remember the power rule that we had before. Anytime you have a number times a log, you can write that as the log of the argument raised to this number. So I can actually write this log as the log of 2 raised to the 4th power using the power rule for logs. And then likewise, I can take this 1/2 and write this log as log of 4 to the 1/2 power. And of course, remember you have to carry the base each time. And then here just bring the 2 down. And then here I can write this as the log of 8 to the 1/3 power. So I have minus the log of 8 to the 1/3 power. Now 4 to the 1/2 power is just the square root of 4. So this would just be the log of 2 base x. And over here, log of 8 to the 1/3 power, that's just the cube root of 8, so that would be log of 2 base x. And also here, 2 to the 4th is 16, so this would be log of 16 base x. Now, these two terms here actually will cancel each other out. Minus log 2 base x on both sides. If you add log of 2 base x to both sides, it'll just cancel both these terms out. And so you'll just get log of 16 base x on the left, and then 2 on the right. And then finally, we can convert this to exponential form and get x squared equals 16. And then if you solve that equation, you'll get that x equals plus or minus 4. But since the base cannot be a negative number, the only answer that works is x equals 4. And I have one more here. I just kind of squeezed this one in here. If you take a look at this problem here, at first it might look like it's a complicated problem, but it's really not that complicated, because if you use your log property, you might remember there's a log property that says when you take a base and you raise it to a log that has the same base, which is common log here has the same base as 10, then you just get the argument of the log. So 10 raised to the log of 2a minus 7 base 10 is just 2a minus 7. So this equation simply becomes 2a minus 7 equals 8, and that can easily be solved by just adding 7 to both sides, and then get 2a equal 15, then divide both sides by 2, and that would give you a equal 15 halves. And so that would give you the solution to this problem, and I believe that's all the log equations that I have. And I've got one more section where I'll show you some applications of exponential and log equations, or exponential and log functions, that is. So we'll see that in the next section.